All right, it's Thursday. Happy Thursday. We're going to talk about the rest of Recursion today. I did push the due date out for Project 1 by popular demand in lab. So that one will be due Tuesday the 5th when we get back from break. So if you're done with it already, great. If you weren't, okay, you got a little more time on it. So let me know if you got questions on that one. And then our next project, Project 2, I wanted to start, should we start that one after break too? Maybe we should start that one after break. So it gives us up to the midterm to do that one. I definitely want to start the group. I think that'll be fine. I think we'll be okay with that. That way you can actually have a break and not have a project to work on. That okay? All right, cool. So let's finish up talking about recursion then. So I did give just the board piece of making the little 2D array or 2D vector in lab. So that's out in the repo if you like it. That's okay. I was just setting that up here just so you could see what it was for the 8 queens puzzle. So we're going to do a similar one. Oh, that's right. I wanted to do the maze solver. Let me go back. I think we're going to finish this maze solver. So this would find a solution, right? When we did our maze solver. I think this one worked for us now, but we weren't able to find like what was the shortest path for it. And it found one solution, found another solution. We hadn't got to the point of, well, which one is the fastest, right? So to do that, we need a way to be tracking that sort of information, right? Which is going to be the shortest path. Now, we could be passing it to all these functions here, right? Because we're calling maze solver that calls maze solver that calls maze solver that calls maze solver. So we could track some sort of information with that of which is the shortest path. It seems a little tedious to do at this point. Would probably work, right? So we could track, we'd have to know how many current steps we have, and then we'd have to know what was the shortest solution we found, right? So I think it'd be easier to do that not having to pass it to this function all the time if we made it into a class. Because a class can have a class level attribute, and then we don't need to pass that integer for, hey, how many steps have I taken every time we call this function? Both ways could work, but I think having a class and just making it available as an attribute would be nice. And then we don't have to pass the maze every time either, right? And because we're passing the maze not as a reference, we're getting those copies going on here. So this is a little bit inefficient in terms of memory use, right? Because we get lots of copies of this every time we call a function, rather than if we write a class for it, we could just have one maze that we're working through. So I think we should try that. So let's see if we can build this into a class then. So I'm going to just add a new header file for it. Try to see if we can keep this organized here. So this will be our maze solver header file. Maze solver, and then maze solver. We need a couple of these things. Do that one, and then we need some of our functions. So we had print maze, can go, maze solver. That one, right? Move those over to the maze solver. So this will be our class for maze solver. On a private section and a public section. So let me just paste this for now for a minute. The private section should probably have this vector character called the maze, right? So we can have a maze attribute we don't need to pass to all of our functions. This will save us a little bit of time here. So we'll need a constructor that takes the maze. So if you give us a vector for the maze, you can set my maze to the maze, right? And then other things like print the maze, or right, we don't need to pass that as arguments anymore because we have our maze attribute. So we're getting a little bit of savings already there, right? Not having to pass that everywhere. So print, yeah, I guess it's okay. Maybe we would want to make a function that return it as a string. Because printing is one thing, but we don't know what this class is going to be used in. Maybe this is so cool, we'll build a web app around it. So it'd be better maybe to turn this into a string, and then we could return a string version of that. So I can say string, do I gotta include string? String. So this will be, I don't know, toString. So instead of couting everything, we're gonna have a string that we're gonna build. So this will be my, I don't know, maze string. Starts as blank, and we'll just take our maze string and we'll append to it. Right? And then we'll take our maze string, we'll append to it. And we don't need the last line there either. Don't need an end line, we can do the \n, right, at this point, if we're doing strings, because we're not counting, so we can't use the endls. But now we have a nice way to get this as a string version, and if I'm running it as a console app, I can put it to the string. If I've got a web app, I can put it on my website somewhere. If I'm doing a mobile app, right, I'll show it on my mobile device somewhere. This can go to, now this doesn't need to be a public function, right? I think this makes more sense as a private function, because no one else should be calling this can go to function. And again, we're saving this now. We don't need to have the maze passed in here, which is nice. All right, so we got that one. The maze solver then, let's see, so we don't need to pass the maze. This one again is probably also a private function. And I don't think that one makes a lot of sense to do as a public function, because they're not going to know what row and index to go find, right? So maybe we just have a public function that starts the solve, or we could even start solving from our constructor. Right? You give me the maze, maybe I'll just go solve it immediately. I don't know if it needs to be a second step. It could be if you want, or maybe just the constructor does it for us. All right, so we don't need the print maze here. We don't need to say we found a solution. Let's see, so we don't need maze there. Maze, 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 maze. Okay, so we took care of all those ones. And all right, now we need to be tracking the maximum, or no, the minimum number of steps to find a solution and our current number of steps. So we can add some more private variables here. So we can have an int for current number of steps. Start off, we'll set that in the constructor, and then we'll have an int for least number of steps for solution, or shortest solution, shortest of steps for solution. I don't know. We make them nice and long, right? So then our constructor should set those. So our current number of steps will be 0, and then the shortest number of steps for the solution. This one's a little messy, right? We probably want something big so that we know if once we find a solution, it will be less than that, right? If it's an int, probably like we can do the max int. We have the max int. Where is it in here? Int 32 max. Is that one it? I think that one's it. So we can just set it to the max if we want, right? That way, when we find a solution, we'll say, hey, is this number of steps less than my current shortest number of steps? And it'll always be yes for this first time, unless you've got a ridiculous 2 billion stepped maze, which our backtracking recursive solution would never find a solution to that anyway. Right? It just won't happen. All right. You okay so far? All right. So then as we're doing our maze solver then, right, we need to start counting our steps. So once we find a solution, we can say, hey, if my current number of steps is less than the least number of steps, so minimum shortest number of steps for solution, then we have a new shortest. Right? If it's less than, set it. Great, now I've set that one. Otherwise, let's go do this thing here. So I'll take my current number of steps plus plus every time I make a step. So every time I leave a breadcrumb, count that as a step. Right? And then once we're done, right, once we've tried all of these possibilities here, I want to undo the changes that I made. Right? You said you didn't really like it having the breadcrumbs there, because it kind of made it a little bit messy. So we can undo the breadcrumb and take away our step. I like having it in reverse order. It just makes me happy. It's not any difference at all, but we'll take away the step and say, hey, let's go back to a space here as I'm undoing my step. So I'm going to try my first location. I'm going to go up, down, left, and right, or what do we say? Up, right, down, left. After I've tried all 4 of those, I'm going to say, okay, well, undo that step. Take the breadcrumb back off and uncount it. Pretend like I didn't step here. Go back to where I was before and let it try its next step here. All right, so we've got toString, we got the maze solver. Let's see, so we want, so printing it, when we undo, it's going to just stop. That is a bit of a bummer. So we won't actually be able to see the solution, I guess, each step of the way. Maybe we still want to be able to see out it. So I think just printing it is not going to, if we undo our steps here, eventually we'll undo once we find the solution. Or if you want, okay, I got it. So let's do this. Let's add a string here for shortest solution. So we can save the shortest solution here. So we'll say our shortest solution is empty string for now. And then if we find a shorter solution, we'll take our shortest solution, will equal the toString, turn our maze into a string. And I can save this one here. And then maybe toString just returns that, returns the shortest solution. Because now we're going to save whatever that shortest path was. So once we find an end, if it's the shortest path, save that string version here to our maze. So then what we need to do then is go find the start. So we should be able to find a start here. So for int row index is 0. Oh my goodness, row index is less than, we want maze.size, row index plus plus. And then for int column index, 0, column index is less than maze dot at the row index dot size. So we probably will assume mazes are squares, but if I don't go off the length of the row, if someone gives me a rectangle, it's not going to work. Right? So I should, if I'm looking for every column, I should be looking at the length of the row, not the number of rows. Right? Just to make sure. So if you give me rectangles, this will work. You could even give me longer vectors in a couple of the rows and then shorter vectors in some of the other rows, and I get this like jagged kind of shape. And we should be able to handle it here. All right. So if my maze dot at the row index dot at the column index is equal to a s here, we're going to call maze solver solve at the row index at the column index. Right? When we find a start, now we can start doing the recursive step here. So just by passing a maze to the constructor, we're immediately going to go try and solve it here. Right? And then maybe we want to add another Boolean function here just for fun, you know, like has solution. So we can return my shortest number of steps for solution, or maybe the shortest solution does not equal a blank. Right? Or we could say, hey, my shortest number of steps does not equal int32 max. Either one we want to compare should be able to tell us whether or not we have a solution without having to have another variable for it. Right? We could have a Boolean and go set that Boolean value, but we could just check, hey, if I don't have a string of my shortest solution, right, then I don't have it. Maybe we'd want to set that to like not solve. I don't know. Maybe we could set that to not solvable in case you wanted to toString every map, every maze, but that's okay. This should be enough. All right, so then in our main function, we need to make a maze solver then. So maze solver, given a maze. We got to go include, right? Include maze solver h, there we go. And then I should be able to print it out, right? So we can see out my solver dot toString. That should give me the shortest possible solution. And then we probably also want to know what that number of steps was, right? Probably need a function for that. Int get shortest number of steps for solution. And we return that value. So shortest solution is a solver dot get shortest number of steps. Something like that. Let's see if it works. Shortest solution is 7 steps. Okay, well we got 7 steps, but we didn't get the maze. All right, so we should have been returning the shortest solution. The shortest solution should have been set to the toString. Oh, I did a bad thing. We didn't turn our maze into a string. I changed it, so now when I toString, I just get the blank back here. That's a bummer. All right, so we got to put that back. I think we've got. Let me go check the GitHub here. I think I've got a version of it out here already. Let's go back to what's in GitHub here. This will be fast. And take this and edit it again. Where did it go? Here's the print maze. There we go. This was the loop we need. So maybe we make that a private helper function, I guess. I don't know, string, or just put it in here, I guess. Right, we can just do the loop. Equals blank. And then for vector in the row, for char in the space, we'll take our shortest solution. Plus equals the space. Plus equals a new line. There. How about that? Now let's try it. Hey, all right. So shortest solution was 7 steps, right? 1, 2, 3, 4, 5, 6, 7. 7 steps, right? So found a better solution than going down and around. Because we've got these values that we're storing at the class level, makes it a little easier for us, right? I like using classes. Classes are great. That one feel okay? So just a couple tweaks here. So we can go and commit that here. So here's the maze solver as class. Oh, what did I do? Oh, that was the lab. That's right. All right. So we did the maze solver. Should we do another backtracking recursion solution? Want more practice? Of course we want. That's always fun, right? Let's do another header file here. Do you folks like Sudoku? Sudoku?
Probably been playing that for like 8 hours in the plane on Saturday.
So it's good. So let's make a Sudoku. Probably, am I spelling that wrong? Sudoku? No, Su? Okay. A private section and a public section. So for Sudoku, right, it's the grid of 9 by 9, and it has the numbers 1 to 9 in every row, the numbers 1 to 9 in every column, and the numbers 1 to 9 in every box of 3, sub-box of the 9 to 9. So we can make a backtracking recursive solution for Sudoku by just trying a number, and then going to the next open space, and trying a number, going to the next open space, trying a number, and if it doesn't work, we go to the next one, right? So if we just look up a Sudoku, let's just look up an image real quick for us, like this one here. So our English version of this algorithm says find the first open space, try the number 1. Or for the numbers 1 to 9, try the number. Once we've tried number 1, or once we've tried a number, and we come back and we're not solved, try a different number. If we're solved, we don't need to do any more work. We can just stop here. So we'll try the number 1. It looks like it can go. Sure, so we'll go to the next open space. We'll try the number 1. No, we can't put a 1. We can't put a 2. Can we put a 3? Sure, we'll put a 3 in. We go to the next open space. All right, we can't do a 1, 2, or 3, or 4. Let's try a 5. All right, a 5 goes in. Go to the next open space. We can't do a 1, 2, 3, 4, 5. How about a 6? Can't do a 6. Can't do a 7. Can't do an 8. Let's put a 9 in here. All right, put a 9 in here. Let's go to the next open space. Can't be any of the numbers, so that was no good. So we come back and we undo. So okay, undo that step. We couldn't put that number there. Make sure we take it out. It didn't work for us. We hadn't found a solution, so we come back here. All right, well, we had tried the 5. Now let's try a 6. Let's try a 7. So it just brute forces every single possible solution, and when it finds a dead end, it backtracks. Just takes a step back. So that's the backtracking solution piece for it here. So we'll have a, we need some vectors and boards here. Let me go steal those from Maze Solver. And namespace, there we go. So we need a vector of vector. Now, we could do chars, and it would be fine. We could do numbers. Numbers is probably a little easier here than trying to make all these chars, right? So this will be the board. And then what else do we need to track? We need to know whether or not we have been solved or not, right? Because once we found a solution, we want to stop. Like with the maze solver, we said, let's just find every possible solution, find the shortest one, and let's keep on undoing. We might be able to do that with Sudoku, but there's no point in trying other solutions once we found one. I don't know if there's actually multiple ways to solve it or not. I feel like there's probably not. So there's probably only one solution. So trying all the other numbers would be a little bit silly, right? And that's actually a lot of work that I would have to do, because it's like there's 81 squares, and each of them could be 9 different values, right? So is that 9 to the 81 possibilities? If we brute force it, it's probably a pretty big number. We don't want to have to do that. We want to find a solution and stop, right? So we'll set Boolean for is solved or not, and then we'll figure out what else we need. So we'll make a constructor here that takes a board, and we'll say my board is the board, this board is the board. Okay, and then probably want to do the toString and has solution or something. I mean, I think they're probably all solvable. Maybe they're not. I don't actually know how well that works. So toString, we could just return the string version of the board, probably. Once it's been solved, I think that should be fine. So we'll steal this one here. String for solution. This will be in the board. And then we can return the solution. Do we have a board? We have a board. Oh, vector of int. There we go. Int. And an int here. Now, if that's an int, I think we can add it to the string. It will probably be okay. We'll see what happens here. If we want to make it look pretty, we can make it look pretty, but that might be a little bit more work. It's probably not too bad, right? I think we did that for the lab. We made that one look a little bit pretty. Let's see. So we did for lab 6. Yeah, this would make it a little bit prettier here. Putting a little border around it. Let's try that. All right, so we need a string solution. Can equal that, right? Let's see. I think that was only 8. So I'm going to need 2 more maybe. And then a new line. And then for each vector is an int here, for row on the board. For each int in the spot here, we'll take our solution and we'll add in pipe character and a spot. And then we'll take our solution and a pipe and a new line. And then add in this one as well with a new line and 2 more dashes. It's probably going to be pretty close. We'll see. We can return that solution. Or board, I don't know, whatever you want to call it here. All right, let's see if that one works first. So we need a 9 by 9 vector here. Let's do, this will be our board. There's a vector of int. So what do we have here? We had, all right, so we need 9 blanks, right? Oh, I guess zeros are going to be silly there. Are spaces better than zeros? That's fine. We'll just do zeros. So a 0 can represent nothing for us. So there's 5, 6, 7, 8, and 9. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 8, 9. All right. All right, and then we had 7, 6, and 2. And then we had 2 and 8. Then we had 4, 6, 8, 9, 7, 1, 5. 4, 6, 7, 8, 1, 9, 5. Was that right? 4, 6. Nope, 4, 6, 8, 9. Totally messed that one up. 1, 7, 1, 5. All right, that's probably enough for now. We'll see if the rest comes out later. So we'll make a board then. Make our Sudoku solver. Sudoku solver. Given the board, we'll include our H file. And we'll see out our solver.toString. See if we get something that looks like a Sudoku board. Uh-oh, what do we get here? Oh, we already had a solver. So this is our Sudoku solver. Missing a couple pieces here. Oops, a couple new lines. Why didn't it get our new lines here? Where are we adding new lines? We're adding new lines. Why didn't they give us new lines? I'm sad. Shouldn't we have gotten some new lines? Something's not happy here. Factor in the board. Solution for each row, for each spot in the row. Add the spot. It should have a bunch of on the board. All right, I don't know. Let's run the debug mode, see what it's doing here. So we have our this, our board. All right, so we got some values there. That's good. Got a bunch of values. Should get our solution. Let's, no, what? What just happened here? Why? Okay. I don't, it like jumped to the end there for some reason. I don't know what happened. Can we just leave this? Let's put this as a watch. Solution. See what happens to it as it goes. We've added more pipes. More pipes. Why are we adding the 0? Isn't spot? Yeah, spot should be 0. Oh, it's not doing the appending here. So we need this like as a string. Is it a I to S or something? Something like integer to string. What was that? Plus int to string. Oh, just toString. Okay, sure. toString for the spot. Let's try that. Take out our breakpoint. All right, now we got some numbers. We're not getting the new lines here. Where did we get the new lines? Or these ones here, right? We're rowing the board. Did I not give it the right? It has commas, right? It's our solution. Oh, goodness gracious. I have a plus sign.
I was just about to tell you.
Oh man, I've not had enough coffee yet today. This is why we shouldn't do these early in the morning. There, all right. Hey, look at that. Looks like a Sudoku board, sort of. Bunch of zeros, but that's fine. We should maybe, if it's a 0, leave it as a space. Would that be fun? So hey, if spot does not equal 0, do this. Otherwise, just do it as a space. What about that? Would that be fun? That'll be look a little prettier now too, right? Look at that. That's even prettier. All right. That took 10 minutes to get a toString, but that's okay. It's good practice. Now, how do we solve this thing? Right? Well, we said, what's the recursive fix? Well, we need to find every square and try it. That's all we have to do. So we can start that probably as a private helper function, right? And maybe we tell it which row, which column we're currently at. It's probably an easy way to do that. Yeah, let's see. So we can make a little helper function. So void solve takes an int row index and an int column index. Now, do we need the row and column? I'm not sure we actually do, because we could just go try and find them here. I don't even think we need that, right? So we'll just say for int row index is 0, row index is less than. Now, probably board.size. I don't know if this works with larger Sudokus, but probably it could, but then, I don't know, maybe it will. Row index plus plus. Do they make 10 by 10? I think that would screw up all of our logic here, but that's okay. We'll do it for int column index is 0, column index is less than board.at the row index dot size. And it probably won't work if these aren't squares, but it's just a good habit here. Then our column index plus plus. Column index. Really? Not going to give me the type ahead? Okay, that's fine. All right, so for each row, for each column, if my board.at the row index dot at the column index does not equal 0, or if it does equal 0, right? If it is a 0, then we're going to start trying here. Right? If I found a 0, let's try a solution. So we can say for int, I don't know, number is 0, number is less than 10, number plus plus. Let's try it. Let's set the board at the row at the column equal to the number, and then recurse. Once we're done, right, let's undo that because it didn't work, right? Put it back to a blank. Back to 0 when we're done. Right, there's our recursive piece here. Now, we probably need to make sure we can find what our base case is, right? Because none of them are going to be equal to 0, right? So maybe we want to check to see if we've been solved or not, right? I guess is solved is actually easy enough to check here. I don't even know if that needs to be a Boolean because we can just determine if we have any zeros or not. Right? If there's no zeros, it's probably solved. Probably. Oh, you know what? We didn't actually check to see here, right? So before we do that, right? If can place number at the row index. There we go. Sorry, I missed a step. Number at the row index at the column index. Then we'll place the number recurse. That's a helpful piece here, right? You don't want to put a bad number in there. Got to make sure the number is good here. And then we'll figure out if we're solved or not. So maybe we'll add a little private helper function for is solved. So let's loop through here. And if we find a 0, we're going to return false, not solved. If I've looped through every row and every column and I haven't found a 0, I return true. It must be solved. Is solved. Right? Check for a 0. There's probably a faster way, right? We could use the search function, but I already had this loop written here, right? We could say for each row, search for a 0 if you find a 0, right? We found some of those cool algorithms we can use. This is probably fine though, right? Could use a cool STL function to search. All right, so we can tell if we're solved or not. So if we're solved, we don't want to do anything then, right? If we're not solved, then let's stop. Or really, after we call solve, don't reset if we're solved, right? We want to leave the solution there. So if we're not is solved, then I want to fix it. If I did find a solution, don't put it back to a 0, right? Because I want to leave the board changed as it was. Does that make sense? Right? I would want to undo if I found a dead end. And a dead end means I still have a 0 somewhere. So I'm going to check to make sure I didn't actually solve it before I undo. Because my 81st move will be the solution. Right? Once I find the last, when I find 99, whatever number fits there, if I can put a number there, I found a solution. If not, I have to start undoing. So undoing puts them back to 0s. And then we're just going to try the very next number, right? And try the very next number, try the very next number. All right. Okay, so we got that. So now we need can place number. So this one is a little bit trickier here. So can place number, give it an int for number, give it an int for the row index, give it an int for the column index. Okay, so right, it has to be unique in its row, it has to be unique in its column, and it has to be unique in its 3x3 subgrid. So the subgrid part is the hardest piece, right? When we look at one of these, right, the sub 3x3s, the rows and columns are pretty quick, right? So we can do some little helpers for that, right? So Boolean can place number in row, give it an int number and an int row index, right? So if we can put the number there, if it's not already found. So for int index is 0, index is 0, index is less than 10, index plus plus. If my board dot at the row index dot at the index is equal to the number, return false. Right? I'm always checking the exact same row. That's not going to change. But maybe I should call this column index. Do that. Column index. So if that column, right, is the number, I can't put it there. So if I've checked all of them, I can return true. Life is good. We're good to go. Right? Same idea with can place number in the column. Can place number in column. Give it an int number and an int for column index. Now, similar idea here. But now this is going to be my row index. Right? I'm going to check every row at the row index, at the column index. If I match here, right, return false. Otherwise, yeah, I'm good to place it here. I didn't find it in that column. So column is fixed based on the argument. Row will change based on my loop here. Right? And maybe should use the board size, board.size. It doesn't really work other than that, but I'm feeling a little bad here. So board.size. Probably should go off a size. So magic numbers are a little bit ugly sometimes. All right, so those ones are okay. But then how about can place number in subgrid? Given an int number, the int row index, and the int column index. Okay, now the trick to this one here is just a little bit of arithmetic. I need to essentially do a 3x3 search, but I need to start at the top left of each of these subgrids, right? So I need to start at this one, search 3x3, start at this one, search 3x3, start at this one, search 3x3, or this one 3x3, this one 3x3, right? Excuse me. So to find that, if the number is 0, 1, or 2, I'm starting at 0. If it's 3, 4, or 5, I'm starting at 3. If it's 6, 7, or 8, I'm starting at 6 for my indexes. Right? So we'll just sort of do this math style. Okay, we'll make a little table here. So this is the starting index. So you're going to start at index 0 if you're a 0. You're going to start at index 0 if you're a 1. You're going to start at index 0 if you're a 2. Right? You're going to start at index 3 if you're a 3. 3 if you're a 4. And just work our way on down, right? That makes sense, what we're looking at? Our starting index and the actual index. So do you see any sort of arithmetic we could do that gets us here? What if we divide by 3 for 0, 1, and 2? Divided by 3, it gets me 0. 3, 4, and 5 divided by 3, well, that gets me a 1. What if I then multiply by 3? So divide by 3, multiply by 3. Zeros times 3 are still zeros. 1 times 3 is 3. Let's check it out. Does it work for the last one? So we should get a 6 for 6, 7, and 8, right? A 6, that should have been a 6 there, a 6 for 7, and a 6 for 8. So divided by 3, 6 divided by 3 is 2, 7 divided by 3 is 2, 8 divided by 3 is 2. 2 times 3 gives me a 6. Right? I've done this before, so that I've seen these sort of patterns, that's all. But it's just some quick arithmetic there, right? Nothing super crazy. So we need the int for the starting row index is going to equal my row index divided by 3, and we want integer division, right? We want the integer division to happen here. We don't want to get a decimal place, right? So we like that it's an integer. Multiplied by 3. And then the starting column index is equal to the column index divided by 3 times 3, right? You know, it looks really silly to do that, but we get that rounding, right, when we do integer division. And then I can say for int row index is equal to the starting row index. Row index is less than the starting row index plus 3, and then the row index plus plus. Right? We could do a little for loop here, and then another for loop, right, for my column index. Column index is equal to the starting column index. Column index is less than my starting column index plus 3, and my column index plus plus. Right? And then it's the same thing here. If I found it at the row index at the column index, false. If I've checked my entire subgrid and I didn't find it, I can return true. Right, so this finds where do I start my 3 by 3 checks. Check 3 rows and 3 columns from each of those corners. Right, so in any one of these values, right, when I divide by 3, multiply by 3, so if I was at, so this is 0, 1, 2, 3, 4. So this is row 4, column 7. Right, so row 4 divided by 3 times 3 should give me 3, will be this row. And then 7 divided by 3 times 3 would give me 6. Right? So I'm at 3, 6 here, row 3, column 6. And I'm going to check for 3 rows and 3 columns. Should work. So can place number then is going to return can place number in row, given the number and the row index, and can place number in column, given the number and the column index, and can place number in the subgrid, given the number, the row index, and the column index. Right? We're just doing that functional decomposition. That was one of my favorite words. Right? Taking a big problem, breaking it down, and decomposing it into smaller and smaller and smaller problems. Right? That's what we did with this one. So I think it should solve then. So the last thing we need to do then is just call solve. Set the board and solve. Eventually we should have a solution. Should we try it? Uh-oh. Let's see. So we got a pause button here. We can do pause. A bunch of calls. That's kind of what we expect. So can I place a number in a column? What number are we looking at here? Let's see. So what is number? Number is 4. Column 4. What's our board look like right now? Oh, we can get rid of solution. I don't need the watch anymore. Let's close out watch. There we go. So here's our this, right? We have our board. We've got some values. Oh, we have a 0 in here though. Where's our can place number? What's this one here? I'm trying to see what these values are. Okay, so we're at row 5, column 4. So I shouldn't have had a 0 in here. That's really weird that I'd have a 0 up here. So something bad happened. How did you get a 0 there? If the board at the row column is a 0, let's try it. Can I place a number? Huh. This is solve 5, 4. So 5, 4. That's a 0. Okay, that's good so far. So we got value. How do we have values in here? So something's screwy. Something isn't right here. Because we shouldn't have numbers later on, right? Because we're kind of going in sequential order here. So we're skipping something. All right, okay, that's all right. So let's see. So let's do this. That's the toString for the solution. So every time I call solve, let's see out the toString. And then line here. We'll sort of do not a debugger here, but we want to see what's happening here step by step by step as it goes. Let's run it for a little bit and then we'll pause. All right, so, oh, I didn't catch it soon enough. Oops, let's see. Let's put a breakpoint there. And we'll just do a bunch of them here. And see if we can see where it's getting hung up. Okay, there's a bunch of them. So we can put a 1, that's what we expect. We put a 3, okay. 2, so this first column should, why did that not fill up? Where did it go from here? I totally skipped a spot. Oh, we kept on going. That's right, okay. So my function kept on going because we found a 0 and we're trying all of them here. Okay, this is why we skipped. So it said, hey, let's try it, and then we'll recurse and keep going and call it and recurse and keep going here. But then when it's done, it just goes into the next one. Right? We might have put a 0 back. So I think this loop is bad. I don't think we want to do this. Yeah, this is no good here, sorry. So having the loop inside a solve is no good here. So we want to just solve the next open space. So we don't want to loop through all of these ones here. So let's go, let's do this. We want to find the next open space. Here, let me stop this. So because I'm looping through every time here, right, it gets reset back to 0, and then I just keep on going to the next one, because that's what my loop did here. We don't want to keep going if there's a 0, right? We need to stop it and let the backtracking recursion work. So this is not working for us here. We want to find the first open space. So we'll have an int for first open row index 0, and an int for the first open column index 0. Right, and we're going to go find it. Hey, if I found a 0 here then, I guess we could use break, but that feels ugly, because we'd have to break both loops, and that would be kind of tricky here. So we'll say my first open row index is equal to row index, and my first open column index is equal to the column index. That's even messy too. That's fine. So let's do void solve int row index int column index. No. Yeah, that's fine, that's fine. So then we'll call our solve function given the row index and the column index. And then we'll break. Oh, that only breaks the one loop, shoot. Sorry, I'm gonna go back to what I had. Let's undo a bunch. Put it back in here. We want to stop both loops. Why is that so obnoxious here? All right, let's set these to -1 here, I guess. We'll set the first open row index to the row index, and then the first open column index to the column index. And then I want this to stop, so I can add into my for loop here and say, hey, my first open row index is equal to -1. Right? You can have more than one check in your for loops. It's not very common. I feel a little bad about this. This was not great, but it'll be okay. First open column index equals a -1. So that will stop the loops as soon as I assign it to something here. Then I can go through and do my number given the first open row index and the first open column index. Oh my goodness, too many of these. I should have just renamed them here. Does that make sense? So I want to stop when I find one open space, and then I'm going to do the, let's try number 0 to 9. Eventually I'm going to undo here if we're not solved. Let's try that. I think we'll find a solution now. Oops, discontinue. Nope, uh-oh. Out of range. Really? Index out of range? Row index -1? How did I get a -1? Oh, when it, stupid. All right, I shouldn't try and give it a -1. All right, so all right, okay, I remember. We don't have to do any of that stupid nonsense here. We can just go back. All right, we just want to return. We can just make the function stop, right? If you call return, our function will stop. Given row index, column index. Too many changes, I'm sorry. Let's put it back. So once we're done, once we've tried all of our solutions, right? At the end of that loop, we're just going to return. That'll stop the function. So we're going to try the numbers 1 through 10. Either we solved it or we put it back to a 0 by the time we're done, and we return. That'll stop the rest of the loop from running here. There we go. Wow, I printed way too many times here again. Oops. Let's try that. There's a solution. All right, fix it up here. So hopefully that matches, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so all the rows are good. Should we check the columns? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why does columns seem so much harder? I feel like we probably solved it here. Right? I didn't check them all, but that was getting a little tedious. Right? Is that fun? So this is backtracking recursion. A different example. And you make your change, recurse, and then possibly undo. With the maze solver, we always undid. With Sudoku, we said, only if we haven't solved it should we undo. Right? Like the 8 queens puzzle, once you find a solution, you're done. If you want to find all solutions, you can just always undo and just have it maybe print when you find a solution. I think that was the idea. We can find all 96 if you just let it run. There's not that many, it doesn't take forever for that one, right? Because that's a nice little constrained board. It's only 64 spaces on it, right? Or this one would take a little bit longer, right, to do 9 numbers on all 81 squares. That's a bunch of times. So stopping early here is key here. So stopping after the first 0 it finds. This was the key here. That's what wasn't working before. I forgot to stop before. You look tired. I got a thermos full of coffee. The original Stanley. Did I already make my joke about that? That's an old joke now. All right, questions, thoughts, concerns? Our next project will be on recursion. We'll have a lot of fun. More backtracking recursion. It's a good topic. And then that sets the stage for the later topics here, not discussions. Ugh, discussions are gross. When we get into some of the other data structures here, we need to understand recursion because we use recursion to do other things when we get to some of our data structures, okay? So we got spring recess for a week, or winter break, because it's still winter, although it feels like spring sometimes. I don't know what next week's weather will be like, but enjoy it. Hopefully you've got nothing going on. I did remember or someone had reminded me to push the lab due date out, so the lab is not due the 27th, the lab is due the 5th, because we're pretending that week doesn't happen. So if you need more time in the 8 Queens puzzle, that's fine. When we come back, we'll start talking about templates on the 5th. We can do our lab on templates, talk about the project solution, talk about the next project, and we can go from there, okay? All right, awesome. It's been fun. You folks have a good break.